Hey, physical science kids, Mr. Tima here. Just going to take you through some Lewis dot structures. Now, I'm not going to write everything on here. I'm going to do some highlighting. So a lot of stuff's going to be filled in, so you got to make sure you're paying attention. The issue is when I try to write all this, it gets kind of crazy. So I got to use my filled in notes, and there we go. First of all, the Lewis dot structure. Okay, Lewis dot structures literally mean we are drawing dots. Okay, so if you were able to do the electron configuration in the Bohr model, the Lewis dot's a lot like the Bohr model. You may want to open up the periodic table link on your Chromebook as I'm going through these notes, because it's going to help you make a lot of sense out of them. First of all, you should know the names of these families by now. If you do not know the names of these families, you're going to start getting lost. Okay, noble gases up here. You're going to start getting a little lost because we need to start moving past that. Now, everything in the alkali metals, if you actually drew or did the electron configuration for hydrogen, that'd be 1. Lithium would be, hydrogen would be 1. Lithium would be 2, 1. Sodium would be 2, 8, 1. 2, 8, 8, 1. Okay, and if you drew out the Bohr models, you'd find that they all have 1 electron in their outermost shell. Beryllium has 4 protons, so it has 4 total electrons, or 2, 2. 2, 8, 2. 2, 8, 8, 2. But every time in their outermost shell, they have 2 electrons. Okay, and if you notice, this pattern exists to where it keeps going up by 1 electron in its outermost shell, okay, until we get to 8. Because if you think about it, 2 in the first, then 8, 1, 2 in the first, and then 1, 2, 3, 4, 5, 6, 7, 8. We don't have any more room in the hotel or our bedrooms or whatever, remember? And we go 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so forth and so on. All right, so let's think about that as we continue to move through this. Before we get into here, we're going to talk about something called the merry-go-round method. Now, the merry-go-round's like the horses at the fair, all that kind of stuff. You've probably seen all that stuff around there. For the point of this thing, we're going to start in this spot right here. I also like to think of them as places at a table. There's 8 places or 8 seats at a table. Now, you could technically start at any of these seats, okay? You can start at any of these seats, but for the point of our class, for right now, at this point, we're always going to start here. My answer keys have it built with starting here, okay? Now, with the merry-go-round method, we start and we put, if we had 1 electron, we'd put that 1 electron here. Let's say we have 2 electrons. We'd put the first one here, and then we'd go around the merry-go-round and put in our second electron. But what if we had 3? We'd go 1, 2, come around the merry-go-round, and there's 3. What if we had 4? 1, 2, 3, and then we go around the merry-go-round and 5, or 4, excuse me. And again, what if we had 5? Well, then we'd go all the way around the merry-go-round until we get back here, and we'd have 2 people sitting at this side of the table. Okay? And again, if we had 6, we'd have these 2 seats filled. If we had 7 electrons, we'd have these 2 seats. And then if we had 8 people, all of these seats would be filled. So for example, if we look at, and remember, we need to understand something, that the Bohr model takes into account all the electrons. The Lewis dot structure is only the outer shell, or outer shell ones only. Okay? So for example, if we looked up here again, we said hydrogen. Hydrogen has 1 outer shell electron. Okay? So it has 1 total electron. So we know we'd put that 1 electron right there. And it has 1 outer shell electron, so we put that 1 here. That one's pretty easy, okay? Helium, okay, has 2 electrons total. So 1, 2, which fills that shell. And then if we did the merry-go-round, 1, 2. Now you're going to notice it says this is not right. We'll cover it later in the notes. But for right now, we're going to follow along as if we didn't know any better. All right, lithium. Coming all the way back up here. Where's lithium? Well, lithium's right there. Okay, lithium has 3 total electrons. 3 total electrons. Okay, so 1, 2, 3 total electrons. 2 in the first. So if we did the electron configuration, we'd write 2, comma 1. 2 in the first, 1 in the outer shell. and then we're going to put that 1 right there. Well, look at that real quick. That Lewis dot looks a lot like hydrogen, which it should because they're in the same family. Okay? Boron. If you look at boron on the periodic table up there, you'll notice it has 5 electrons. It has 5 protons, which equals 5 electrons. If we did the electron configuration, that'd be 2, 3. All right? 1, 2, 1, 2, 3. Now, follow the merry-go-round method. This is where it changes. There's 1, 2, 3. And again, if we had 4, we'd put it there. But we don't have 4. We only have 3. This is going to become very important very shortly. Oxygen. Oxygen, if we look up at the periodic table, has a total of 8 electrons. Because it has an atomic number of 8, which means it has 8 electrons in this case. So it would be 2, 6. That's back to electron configuration. 1, 2, full. 1, 2, 3, 4, 5, 6. And now we're doing the merry-go-round. 1, 2, 3, 4, 5, and 6. Now again, if you come all the way back up here and look, if you just look without doing all that stuff we just did, if you notice 1, 2, 3, 4, 5, 6, we know right now it has 6 outer shell electrons. So we can fill in and do the merry-go-round to get it 6. All right, let's try neon. Now neon's in family 8, but it has 10 protons, which equals 10 electrons. Okay, 2, 8. It's in family 8 because it has 8 outer shell electrons. But even if you didn't know that, we'd go 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And it's all full. And if you notice, if you came over here and did it in the Lewis dot and follow the merry-go-round, you're going to notice that it has 8 and it's full. Everybody has a place at the table. That's how we know it's full. So, that word valence electron is literally the number of electrons in the outermost shell. Now, what's important is this part right here that says the unpaired electrons are responsible for bonding. So think of the seats at the table like the bonding areas. Okay? If you went up to sodium, which is in family 1, you'll notice that sodium only has 1 outer shell electron. Boron's in family 3. It has 3 outer shell electrons. Nitrogen is in family 5. It has 5 outer shell electrons. And fluorine has 7. So it has 7 outer shell electrons. What's important to notice, and that's the part you should understand at this point, is how we got the number of valence electrons. By looking at the periodic table, looking at their family. I mean, you could go through and do the Bohr model and all that stuff, and that's fine. Okay? But notice, how many bonds could sodium make? How many bonds can sodium make? Well, it could make a total of 1, 2, 3, 4, 5, 6, 7 other bonds. Boron could make up to 5 bonds. Nitrogen could make up to 3 bonds, and fluorine could make up to 1 bond. This is going to be important as we go to the next chapter. So again, what makes noble gases stable? Well, what makes them stable is if we go back to neon like we talked about earlier, it has 10 protons, which equaled 10 electrons, which equaled 2, 8. All of its rooms are full. 1, 2, that is full. 1, 2, 3, 4, 5, 6, 7, 8. That room or that floor is full. If you look here, there's no place at the table to be attacked. All the friends are buddied up. These guys are buddies, these guys are buddies, these guys are buddies, and these guys are buddies. There's no place to attack. That's why we say they're stable. So, going all the way back to what we talked about at the very beginning, if you look up here and you go, well, there's neon right there. And it's part of the noble gases, which are said to be stable. Helium is right there. Now, some of you might be thinking, helium has 2 protons, which means it has 2 electrons. Well, all of these have 2 electrons. So why isn't helium here? Here's the reason. Here's the reason why helium is here and not here. Okay? If we go back down here and we actually look at what helium is, we have to understand, because the first shell can only hold 2, it is now full, which means it is stable, which means it cannot be attacked. This is not right. You are not allowed to go 1, 2. That's not right. Because it is a noble gas and it is stable, we have to pair up those electrons. This is not right. Why not this? Because 2 unpaired would mean that it could make 2 bonds. But it can't make bonds because it is a noble gas. So at the end of the day, we can then look at this and say, and you should know when you're done with this, first of all, you should know all these names, no biggie, you should know those names by now. But you should know the first family has 1 outer shell electron. The second family has 2 outer shell electrons. The 3, 4, 5, 6, 7, 8 have that corresponding number of outer shell electrons, except for, really, the one exception is helium. It only has 2 outer shell electrons, but it's part of the noble gases, so we say it's full. You may have noticed that I have these other dots up here that have been saying 1 plus, 2 plus, 3 plus, 4 plus or minus, 3 minus, 2 minus, 1 minus. Well, or 0. Okay, these are called ionic charge numbers. If you think about it real quick, and we're not there yet, but if you think about it and actually think about this, for some of you that really get what's going on, if everything in family 1 has 1 outer shell electron, for it to be stable and get to a full outer shell, it would want to give up 1 electron and become more positive to become there. We're not quite there yet. Don't worry about it. These guys right here has 7. It would rather gain 1 electron or become 1 more negative to be like a noble gas. Again, don't freak out if you're not there yet. We haven't covered that yet, but we will be getting there. And other than that, I